Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers, and I'm going to show you something new with our new remote. All right, let's see. I got this. Oh, there we go. That's me, Dr. Frank Summers. This is a special remote that I can use to highlight sections on screen. Our webcasting audience does not get to see the laser pointer when we use the laser pointer. So I'm trying out this for the first time tonight, and if it works successfully, maybe we'll be able to get our speakers to use it in the future, and the webcasting audience will see all of our highlights. Let's see, when you came in, there are images on the table. Tonight's image is of the Ring Nebula, NGC 6720. And the Ring Nebula is one of the most beautiful planetary nebula. It has nothing to do with planets. That's just a name that unfortunately stuck. It is a dying star. If you want to understand it, well, you can turn over on the back and you can see that we have a collection of a few paragraphs that can tell you about it, as well as up here in the upper right-hand corner, there are comparisons to other planetary nebulae. Planetary nebulae have some really, really cool shapes. It's well worth investigating. We have to do our reminder. Please silence your phones. We don't want them going off during the lecture. Thank you very much. Because tonight's lecture is one you are definitely going to want to listen closely to. It's called Our Colorful Universe, Translating Cosmic Light by our very own master image processor, Joseph DePasquale. Upcoming, we have an August Tiny Stellar Islands in a Big Old Universe. This will be a talk about dwarf galaxies, okay? And dwarf galaxies, you might think, who cares about them? You know, Snow White may care about the 7 dwarfs, but why would we care about dwarf galaxies? Well, they are the most numerous type of galaxy in the universe. They're actually extremely important to understand how the universe develops. In September, Brandon Lawton is going to talk about the Astronomer's Toolkit. He's decided he wants to talk to you about all the various tools astronomers use to investigate the universe. And that should be fun in September, right after Labor Day. And in October, a perennial fun topic, black holes and gravitational waves. We have learned so much about this brand new gravitational wave astronomy. And Emmanuel Berti from across the street at Johns Hopkins will be discussing that. If you want to find out about things, you go to our website, and you will find that our website has a brand new look. It doesn't have, unfortunately, a short URL. So if you want to go to the website, it's https://hubblesite.org resources-gallery learning-resources public-lecture-series. Easy to remember, right? Take a picture of the screen. If you put into your favorite search engine Hubble Public Lectures, you should end up at this web page, okay? We have on it our list of our upcoming lectures. We have the links to our past lectures. All right, so if you want to go to our past public lectures, as well as our YouTube playlist and our webcasting archive where you can watch them. We also have the lecture announcements email list where you can enter your email address and subscribe to the lecture announcements. It's basically 2 emails a month reminding you of the upcoming lectures and telling you where the webcasts are posted. Finally, they have a new setup for presenting the lectures. This, for example, was last month's lecture by Christopher Britt, and it includes the basic information. It now includes the description, okay, as well as link to the webcast on the STSCI site and the link to the webcast on YouTube. Okay, so they have new stuff on our website for you to look at and get all the information about our series. Okay. The email, I showed you how to sign up to the website. If you find yourself that you do not want to do that, and you want to just write it down on a piece of paper and hand it to me, that'll work as well. Those who have comments and questions can send them to publiclecture@stsci.edu. If you like social media, we have social media for the Hubble Space Telescope, for the upcoming James Webb Space Telescope, and for our institute, the Space Telescope Science Institute, on Facebook, Twitter, YouTube, and Instagram. And if you care about what I might want to tweet out, I'm on Facebook and Twitter, but I will warn you, I only do that occasionally because I get very busy in my job and I enjoy my job, and I don't do as much social media as perhaps I should. The observatory across the street at Johns Hopkins will not be open tonight. They said it was looking like there could be showers and thunder showers, and things were not set up properly for it to handle this, and so there will be no observatory tonight. However, I always note that they do have open houses on Friday evenings. If you go to the Maryland Space Grant Observatory website, you can see the observatory status right there, okay? That observatory status will be updated on Friday evenings about 6 p.m. They tell me if they're going to be open, so you can come down and see it then. All right? Well, we took a long time here doing some extra stuff here tonight, so I have my news from the universe for July 2019, but I'm only going to give you one story here tonight, okay? And our only story for tonight is the intriguing atmosphere of a mini Neptune. All right? So, in our solar system, we have our Earth here on the left, and we have Neptune on the right. And these are kind of roughly to scale, or as simple as to scale as I can make it very quickly in PowerPoint. And so Neptune's diameter is 3.9 times Earth. It's about 4 times the size of Earth. And its mass is 17.15 times Earth, okay? So Neptune is a giant planet. And some people call it a gas giant, but actually, if you're a real astronomer, you call it an ice giant, because Neptune is 30 times further away from the sun than Earth. It formed out beyond what we call the frost line, and it formed with a lot of ices falling onto it, okay? So the composition of Neptune's atmosphere contains a lot more heavy elements than it otherwise would if it had formed closer in, where Jupiter and Saturn formed, and those are commonly called gas giants. Okay? That's important because this discovery is about a planet called GJ 3470b. Okay? And this is what we call a mini Neptune. Its mass is 12.6 times Earth. So it's not quite as big as a Neptune, but it's much bigger than an Earth. Right? We often have, has anybody heard the phrase super Earth? Okay, yeah, okay. The super Earths, generally we think of those up to 5, 6, 7, maybe 8 times the mass of Earth. So this is sort of larger than a super Earth, but it's smaller than a full-size Neptune. So it's starting into that in-between phase, okay? Is it an Earth-like object? Is it a Neptune-sized object? At 13 times Earth, I consider it more of a Neptune object, so I would call it a mini Neptune. All right? And they have measured the atmosphere of this object to have a hydrogen-helium atmosphere with a rock and ice core. And at first, that's not really surprising. But let's go a little further. This planet has been discovered around a red dwarf star, GJ 3470, okay? And whereas I told you that our Neptune is out beyond this frost line, out at 30 astronomical units, this one is in so close that it orbits around its star every 3.3 days. Okay? It orbits this red dwarf star in 3 days. Furthermore, it's not situated like this from our point of view. It's actually situated from our point of view where it passes in front of its star and behind its star, and in front of its star and behind its star. When it passes in front of its star, it's called a transit. When it passes behind the star, it's called an eclipse. All right? And the Hubble Space Telescope and the Spitzer Space Telescope have been observing this planet star combination during, let's see, what's the notes? They say like 20 transits and 12 eclipses, or is it the vice versa? I don't know. So you put the two together. You've got this mini Neptune-sized planet passing in front of the red dwarf. And in these transits and eclipses, you can take it when it's in front and when it's not in front, subtract off the spectra, and get the atmosphere of the mini Neptune. Now, we've done this for a lot of hot Jupiters. We may have done it for a few Neptunes, hot Neptunes. This is, they claim, one of the first times it's been done for a mini Neptune. This is one of the smallest objects from which we're measuring the atmosphere. Now, I said hydrogen and helium atmosphere shouldn't surprise you much, right? Because hydrogen and helium are the dominant elements in the universe. However, this atmosphere is really just hydrogen and helium. It doesn't contain the water vapor and the methane that you would expect for a Neptune. If it was normal Neptune, it formed out beyond the frost line, and then it migrates inward due to gravitational interactions. Okay, planets, we don't expect Jupiters and Neptunes to form close to their star. They only form way out here. And so if it migrates inward, it should still at least keep its chemical composition in its atmosphere, and there should be water vapor, there should be methane. They found no evidence of such. And as such, it's a weird and odd object. How does it form a 13 Earth mass object without having a good amount of heavier elements in its atmosphere? And that's the conundrum. Now, they make a speculation that's saying, well, perhaps it actually formed in situ, okay? That it formed in close to its star, which I, as an astronomer, start to actually laughed at when it was brought up in the news meeting. It's like, come on, you cannot form a giant planet in next to the star. Okay, that's just not possible as far as I know. Maybe they know something I don't know. But what they've speculated is that the rock and ice core formed first like a Earth size, a very large Earth type rocky planet, and that the hydrogen helium atmosphere then accreted onto it, and that it would have gone much larger, except that this was late in the stage, and it only was able to pull in the hydrogen helium. It wasn't out far enough for the ices to accrete that would have given the heavy elements in the atmosphere. I consider that a bit speculative, but it does make for an intriguing object. That one of the first small Neptune type objects that we measure doesn't have the characteristic atmosphere we expect for a Neptune-sized object. Okay? So, to be continued as we study this more with both Hubble and Spitzer and upcoming space telescopes. All right? Okay. Now we move on to our speaker for tonight. And our speaker for tonight is Joseph DePasquale. He got his degree in astronomy and astrophysics from Villanova University, and then spent 15 years up in Boston at the Chandra X-ray Center, where he became an absolute expert in astronomical image processing, in data processing, in visualization, anything about taking the universe and making it understandable and contributing to press releases. I think Joe can do it, okay? Because when he got here, the first project I worked with him on, I said, here, try something like this, and I've never gotten anybody in this building to be able to really jump in when we worked on the candle stuff together, and he just jumped in and said, oh, I'll figure it out. Bam! He figured it out. So he's been very impressive in his few years here, and he is now our lead image processor, and he's here to talk to you about our colorful universe, translating cosmic light. Everyone, Joseph DePasquale. Whoops. What number are you on? You're on 1.
Oh, okay. Well, thank you, Frank, for that introduction. It was really nice. And thank you, everyone, for being here tonight. It's great to see such a full audience. And hi to everyone out on the internet as well. I think my family's on, too. So our colorful universe, translating cosmic light, is an intentionally vague enough title that I can sort of cover whatever I want, which I like. What I would like to do, though, is to talk a little bit about the methods that I use for processing astronomical data, but I want to frame it in the context of the history of our understanding of light. And so we're going to spend the first, maybe third of the talk talking about the history of light. And before I get into that, I want to talk a little bit about just light in general. I mean, it's the dominant way that we experience our world. Our eyes are constantly flooded with light. But imagine, so light carries information. We're surrounded by information. Imagine if our eyes were actually sensitive to light beyond the visible wavelengths. This is a conceptual visualization showing what it might look like to be able to see cell phone tower signals in a city. So if our eyes were sensitive to this kind of light, we would just see the city blanketed in light. Every one of these buildings basically has a cell tower above it, and it's emitting signals all the time. Or imagine being able to see Wi-Fi signals. This is a visualization of free Wi-Fi signals on the National Mall. Imagine being on the National Mall, sitting on a park bench, and just seeing this swirling around you. It would be overwhelming for sure. Very glad that our eyes are sensitive just to visible light. Of course, we all know, we've heard about the speed of light, 186,000 miles per second, or 3 times 10 to the 8th meters per second. In our light bubble of Earth, that seems instantaneous, right? That's the speed of light travels around the Earth 7.5 times in 1 second. And so in our experiential life on this planet, light is instant. But as soon as we leave that light bubble, that speed limit becomes important. For example, Jupiter, which is up, if the clouds clear tonight when we leave, the light that is currently reflecting off of Jupiter as I'm speaking right now will be hitting Earth when you leave here tonight. So keep an eye out when you go outside for Jupiter. It'll be the big bright thing in the southeast sky. And this, of course, this speed limit to light gets even more significant as we move away from our solar system. As a species, our humanity has been generating radio signals for about 100 years. And that's basically creates a light bubble around our solar system that's been expanding into our galaxy for 100 years. But on a galactic scale, it's pretty insignificant. If I were to ask you to draw a circle on this is a visualization of the Milky Way galaxy. And somewhere in here is a circle that shows how much light has moved through our galaxy in 100 years. You might think it would be something like this, but no, it's that little dot right there. We'll zoom in on that. So when people say, why can't we send a probe up into space to be able to take a picture of the Milky Way from above? That's why. And that's assuming it can travel at the speed of light, which is not possible, of course. It would take millions of years, generations, to be able to do something like that. But now moving on into the history of light, this is what I call a crash course in light. And I'm by no means an expert in this, but there are a few key concepts that I want to touch on before we dive into the image processing part of this. So we've known about and have been studying light for thousands of years, going all the way back to Chinese and ancient Greek philosophers. Of course, the ancient Greeks had this idea called exomission or extramission, the extramission theory of light, which was that our eyes were actually emitting light rays. And so the light that we saw was actually bounced off of objects from our eyes. Of course, we know that's not true. What the Greek philosophers gave us, though, was really the scientific method, a way of analytically thinking about things. Moving on through the Islamic civilization, European Enlightenment, up to the discovery of the visible spectrum with Isaac Newton in 1666. This is where we finally start to realize that light is made up of component colors. And then moving beyond visible light, William Herschel discovered infrared light in 1800. He was doing an experiment where he was actually measuring the temperature of colors of light. So building on the work of Newton, he was able to use a prism to break down light into its component colors. And then he was actually just using a thermometer to measure the temperature of the light. And what he noticed was blue light was cooler than redder light. And so as he went from blue to red, the temperature was going up. But then as he went just beyond red, the thermometer kept rising. So what's going on here? There's nothing there that you can see, but the thermometer is rising. There must be something there that's causing it to rise. That's actually infrared light. There's light there that our eyes are not sensitive to. And now we can thank William Herschel for discovering infrared light. If you have a cell phone with Face ID, that's how it works. It uses infrared light to project something onto your face that basically creates a grid. The phone recognizes your face in that grid and then unlocks your phone so you can check Facebook. Moving on into spectroscopy, Joseph von Fraunhofer in 1814, he develops a method for analytically looking at the spectrum that's generated from a prism. and also discovers the dark absorption lines that we see. If you look at a solar spectrum, you see all these dark lines in there, and that's caused by atoms and molecules in the solar atmosphere absorbing light at specific frequencies. And so this is where we start to move from qualitative to quantitative analysis of light. Building on even further, James Clerk Maxwell, and this is a really pivotal moment in our understanding of light, he discovers this connection. He's studying electricity and magnetism, and he discovers this connection with light, where these fields, these oscillating fields of electricity and magnetism, are moving at what is known as the speed of light, c. And so this is the first time that we draw this connection, that light that we see with our eyes is actually the same thing as electromagnetic spectrum. And that was in 1860. In 1895, Wilhelm Röntgen discovers X-rays. You can see he's being irradiated right before our eyes. He was experimenting with vacuum tubes in the lab and discovered this. He had a tube shining, and across the room there was this material that was photofluorescing, and it was basically X-rays were being shot across the room, hitting this piece of film and lighting it up. And then from that, he goes on to become the father of diagnostic radiology, and he also wins the first Nobel Prize in 1901, which is really cool. And you may notice that the name Röntgen may sound familiar. His name became synonymous with X-rays. So he called it X-rays, but then people, especially in Germany, called them Röntgen rays. And if you've watched Chernobyl, you've heard that a lot. Building on the work of Maxwell in the Einstein era, Einstein discovers in 1905 the photoelectric effect. And this is where we start to have an understanding of light as both a wave and a particle, the wave-particle duality of light. Einstein also wins a Nobel Prize, very cool, for this work in 1921. So now with this sort of rudimentary understanding of our history of understanding light, we now have a framework for understanding how light has paved the way. This understanding has paved the way for astronomical spectroscopy, which is now taking astronomy into a quantitative realm and allows astronomers to start to qualify stars by the nature of their light. We can classify them that way. And so as I mentioned before, this is a really detailed solar spectrum here. And all of these dark lines here are caused by atoms and molecules in the solar atmosphere. And using this information, this is how we can classify stars. But there are other ways that we get information from stars, notably just by their light. And there's a really great example of how just measuring light and its intensity is really important. Not even 100 years ago, we had this concept of the size of our universe that was completely different than what we think today. There was something called the Great Debate between Harlow Shapley and Herbert Curtis in 1920, where Shapley was on the side of saying that our universe was the Milky Way galaxy. Everything, the entirety of the universe, when we look up in the sky, was contained within the 100,000 light years or so of the Milky Way. And Herbert Curtis was arguing that observational astronomers were looking up in the night sky and seeing what they called spiral nebulae. Now, Herbert Curtis theorized that these spiral nebulae were actually island universes or other galaxies in their own right, much further distant from the Milky Way. And so this is kind of what the state of the art was, not in 1920, but one of the first hand drawings of the Whirlpool galaxy. Of course, light was the answer to figuring out the distance and the true size of the universe. And this was through the importance of Cepheid variable stars. These are a type of star that pulsate with a known frequency that is directly related to their luminosity, the amount of light that they give off. Henrietta Leavitt at the Harvard Observatory discovered this. She called it a period luminosity relationship. And so if you are able to accurately measure the period of pulsations of a Cepheid variable star, then you're able to determine the distance to that star very accurately. And just to give you a sort of a down-to-earth example of how this works, let's consider the 100-watt light bulb. Its absolute magnitude, or its intrinsic brightness, is 100 watts. It's printed right on it. Its apparent magnitude is the brightness that you would measure from a distance to that light bulb, okay? And that has a very well-known relationship where the light falls off as a 1 over r squared relationship. So as you go away from the light bulb, the brightness is dropping significantly in this way. And the true equation here, this is how you can derive the distance. Once you've measured that apparent magnitude, and if you know the absolute magnitude, then you can determine the distance to that bulb. So this period luminosity function is essential in understanding the distances to these Cepheid variable stars. So combined with their apparent magnitude, we can now get an accurate distance measurement, and that's exactly how this debate was finally settled. In 1923, Edwin Hubble was observing Cepheid variable stars in the Andromeda Nebula, where he discovered this variable, clearly denoted as var. And using the period luminosity relationship, he was able to determine an accurate distance to the Andromeda galaxy, which was 2.5 million light years, which was way further than the understanding of the size of the Milky Way galaxy at that time, which was about 100,000 light years. So it completely blew open our concept of the size of the universe just through measuring the brightness of light. Back in 2011, the Hubble Space Telescope actually went and looked at that same exact variable star, and we measured a very accurate light curve. And working with ground-based astronomers, we determined a period of 31.4 days for that particular Cepheid variable star. And so for that work and for his many other contributions to our understanding of the universe, we named our favorite space telescope after Edwin Hubble. The Hubble Space Telescope is arguably the greatest scientific endeavor in the history of humanity. For the last 29 years, it has been providing us with breathtaking views of the cosmos and groundbreaking science. Thanks in no small part to the courageous men and women of the astronaut program who went up in 4 shuttle missions, servicing missions, to make sure that Hubble was working in tip-top shape. Hubble has become synonymous with astronomy. It has literally transformed our understanding of the universe, but also our understanding of what the universe looks like. I think of these images as cosmic landscapes, and as an image processor, I approach them as a photographer would, trying to pull out as much detail as possible while respecting the inherent data. Indeed, the further we look, the deeper we look with Hubble, the deeper it gets. And now I'd like to actually explore a little further some of the photographic concepts that I was talking about here. The visual principles that are sort of a guiding force in the work that I do when I'm taking the data from the telescope and turning it into press release imagery. And so the three key concepts that I always try to keep in mind are tonality, color, and composition in these images. So starting with tonality, when we get the data from the telescope, it comes down, it looks basically just black. And that's because the sensors, the detectors on the telescope are very sensitive to light in a way that our eyes are not. There's a huge dynamic range, meaning that the darkest darks and the brightest brights, there's just a huge range of intensity values between the two, much more than our eyes could see, or much more that can even be displayed on a computer screen. And so we have to scale that data. So the first step is to be able to pull out the details of the data. And so in this is a linear scaling of an image, where using a linear scale, you basically just see the brightest points. So the stars, the centers of the galaxies, those are the things that are showing up when you do a linear scale. Now, if you want to pull out more detail and see stuff that's darker than those bright point sources, you need to ramp it up. You need to take that black level and just squish it up there. And so now you can actually see some of that faint detail and that faint structure in the galaxies, the dust structure. But because we stayed with the linear scaling, we've sacrificed the cores of the galaxies and the cores of these bright stars. Now they're all blown out, and we've lost data by doing this. This is completely saturated to white, so you've lost that data. So we need to do a nonlinear transformation to the image to be able to recover the details in those cores, but also be able to see the structure, the faint structure in those galaxies. So a nonlinear transformation, like a logarithmic transformation onto the image, will allow you to see the full range of brightness from darkest to bright without sacrificing anything. So this is a key first step in working on these data. And an example of a tool that you could use to do this kind of thing is this is called FITS Liberator. It's available for free from spacetelescope.org. I don't actually use this tool. I use something called PixInsight. If you're an astrophotographer, you may be familiar with that. Basically, all this does is it allows you to do that kind of transformation, that kind of nonlinear transformation to your data. You basically select the stretch function here. So in this case, it's an arcsine function, which is a nonlinear transformation. And then in here, you see the histogram, which is basically just showing you the intensity values from dark to bright across the whole image. Okay, so there's a lot of really dark stuff, and then there's a long tail to the bright stuff. So the brightest things are these stars, and then everything else sort of shows up in the darkest range. And so you can now stretch that out, and then you can change your white and black points to suit your needs. So now thinking about color and composite color, this is how we get color from these images. Hubble takes images in different filters, and those filters allow certain wavelengths of light to pass through to create images specific to those wavelengths. So when we look through color filters, we see color, but Hubble's detectors see in black and white. And so the images that we get from the telescope are black and white. We need to apply color after the fact to make a color image. And so for the example that we were looking at, this is Stefan's quintet. This is what we call a natural broadband color. The three filters that are here are basically red, green, and blue, essentially the sensitivity of our eyes. That's why we call it natural color. Each filter covers a sort of a broad wavelength range corresponding to blue light, green light, and red light. So we take these data, we've scaled them now appropriately with a nonlinear transformation. Now we apply color to them according to their wavelengths in the filters. And then we combine them together in image editing software, maybe Photoshop, and you get this. Now this isn't the end of the story, and this is where the more subjective aesthetics come into play. So the photographer's eye becomes important here to be able to notice if there's a color cast in this image, if there are things that need to be cleaned up. A lot of times there are artifacts in these images. There are cosmic rays. There are ghosts from internal reflections of the telescope, and all these things have to be taken out of the image for a press release. And so after cleaning all that up and adjusting contrast and tonality, we arrive at the clean press release image using the full tonal range and preserving as much of the color to show off all of the important structures in the image. So for example, the galaxy, the foreground galaxy here, these bright red regions they're called H2 regions. They're pockets of hydrogen gas where stars are forming. And we want to be able to see that clearly in the image. And so it's processed to show that. Now looking at another type of image that Hubble will typically take data on is a narrowband image. And now this is similar to what we were just talking about with the natural color, only with narrowbands, the filters that we use are looking at very specific wavelengths, very small regions of the electromagnetic spectrum. And we're taking an image in each one of those filters and now combining them together to make a color image. But unlike before where we had the sort of natural translation from red, green, and blue based on the filters, in this case, these filters, they correspond to oxygen, hydrogen, and sulfur. If I were to color them according to where they actually exist on the visible spectrum, you would basically get cyan, red, and slightly more red, which creates this image, which is kind of ugly and doesn't actually tell you a lot. It's aesthetically, it's not very nice, but it also doesn't really reveal the true beauty and the true depth of the data. So instead of using the colors as they're assigned in the spectrum, we can apply this sort of RGB mentality to shift wavelengths, shift the filters, and apply blue, green, and red to these as well, as long as it's chromatically ordered so that the shortest wavelengths get blue and the longest wavelengths get red, and then green comes in the middle. So now oxygen becomes pure blue, hydrogen becomes green, and sulfur stays red. But when you combine them together this way, you get this much more pleasing composite image that actually reveals more detail because you've now created an image that has a fuller color range in it and allows more of the data to show off. I mean, I would argue that the wispy details surrounding the nebula here are much more apparent in the image that's RGB. And of course, this is the Eagle Nebula. I probably should have led with that. The famous Pillars of Creation image. And then there's the post-processing step. So here is the basic color combination, RGB, from those narrowband filters. But that's not the end of the story. We will now want to take away the color cast. We want to do additional processing. We want to brighten it. We want to highlight different features. The stars look a little strange. Let's take some of that red out of the stars. Let's emphasize the structure of the pillars of creation themselves, balance the color better, pull out the shadow details as much as we can, and then crop it. And this is where the composition comes into play. These images are, these are objects in space. There's no up or down, although astronomers will argue with that. It must be north up. It doesn't have to be north up. It can be any orientation that works aesthetically if we want it to be. So that's where the photographer's eye again comes into play. So now I'd like to shift a little bit from what we've been talking about with Hubble into more multi-wavelength astronomy. And before I do that, I just want to give you a quick refresher on the electromagnetic spectrum. I've been talking about it a lot, but I never actually showed this graph. I'm sure most of you are familiar with the electromagnetic spectrum. This is light in all its forms, from the lowest energy, longest wavelengths up to the highest energy, shortest wavelengths, so radio, microwave, infrared, visible light, UV, X-ray, gamma ray. It's all there. This is everything. All that we, well, not that all that we see. All that we see is just that little bit in the middle. And that's because our eyes have evolved on a planet that orbits a star that emits most of its light in the visible wavelengths. So as I'm showing these images in the following slides, I'm going to have this handy little guide here to tell you which wavelengths of light are actually shown in that image and how they're colored. So keep an eye out for that. Before I show the images, though, I want to just review quickly the NASA's Great Observatories program. This was NASA's attempt to really broaden our horizons, visually speaking, to take in as much light as possible in all the different wavelength ranges. And they have to be, for the most part, they have to be space-based observatories because Earth's atmosphere is opaque to most of these high-energy most of the high-energy part of the electromagnetic spectrum, gamma rays, X-rays, they're all, and UV are mostly absorbed by our atmosphere, which is good for us. The infrared is also mostly absorbed by the atmosphere. And so we have to put these observatories up in space above our atmosphere. And of course, with Hubble, it really helps to have the telescope up in space because even though the atmosphere lets visible light through, it does distort it. So NASA's great observatories include the Compton Gamma Ray Observatory, which was launched in 1991 and operated until 2000. The Chandra X-ray Observatory, which is this year celebrating 20 years in orbit. Hubble Space Telescope, which is now 29 years in orbit. And the Spitzer Space Telescope, which was launched in 2003 and is supposed to be shut down in January. So why do we want to look at the universe in multiple wavelengths? I like to make this analogy to listening to an orchestra. And imagine that you're listening to the orchestra, but you can only hear the brass section. It's going to be a very different experience. Similarly, when we're looking in space and we're trying to observe the universe and understand it, it really helps to look in as many wavelengths as possible because there's a lot more information there. So let's look at something in X-ray light. Now we're in high energies. We shifted into high gear. This is Cassiopeia A, and it's an X-ray image in red, green, and blue. So following a similar coloring pattern to what I showed you with the narrowband imaging. Now we're applying that concept to X-ray light. We're breaking it down into low, medium, and high energy X-rays and applying red, green, and blue colors to those images. And when you put that all together, you get this amazing image of a supernova remnant, where this bright spot here is a neutron star that's left over after the explosion, supernova of a star. All of that material was blasted off into space and is emitting X-rays. It's very hot, and there are blast waves moving outward, and there's one moving inward. It's called a reverse shock. The highest energy X-rays, which are blue, surround all of the material inside. That's the shock wave moving out into space. There's even this cool jet shooting out to the side here. That's mostly green light that actually corresponds to iron that's emitting X-rays. And that's a really interesting feature. Somehow the star, when it exploded, preferentially shot material out in one direction, and that became the jet moving in that direction. But now we can apply this multi-wavelength concept to it and bring in Hubble Space Telescope data. And if I take away the X-ray data, we get a very different understanding of the supernova remnant. Most of what we're seeing here traces a lot of what we saw in the X-rays, but leaves a lot out too. This is oxygen, mostly. Oxygen that's emitting, that's radiating in visible wavelengths, but also in X-ray. We're back to the X-ray. Here's another one of my favorites. This is the Whirlpool Galaxy. And what we're looking at here is the full color, natural color, broadband, red, green, and blue optical image, and X-rays overlaid in purple. And now this is just a beautiful spiral galaxy that many people are familiar with, that's been a very famous Hubble image, full of these H2 regions, these regions of star formation, full of blue stars, lots of intricate dust lanes moving out in its spiral. But when we look at it solely in X-rays, we see a very different view. Mainly what we're looking at here is hot gas, the hot gas between stars. And all of the point sources here, most of those are actually black holes or X-ray binaries, neutron star, black hole binaries. And of course, there's the supermassive black hole at the center of the Whirlpool Galaxy as well that we're seeing in X-ray light. So all of this is very high energy phenomena that's emitting X-rays, and we're seeing that here. And now we can also apply the three-color method to this and get even more information from the X-ray data. And so now we're seeing that most of that hot gas that we're looking at is actually emitting low-energy X-rays. And it's those point sources that are really the really super energetic, bright white lights of this in this galaxy. Now moving on to one of my favorite images, one of the first images I worked on when I came over to Space Telescope, the Crab Nebula. So this is a supernova remnant, another supernova remnant. They're my favorite. In constellation of Taurus. It's about 6,500 light years away. And this image is actually made up of 5 different wavelengths of light, all combined together. So now we're kind of taking our concept of 3-color and playing around with it. And when I made this image, I really was thinking that way. I was like, I have this concept for how to put together images with three component images, red, green, and blue. How can we apply that to something that has more than 3 channels to it? Well, basically, I just took the color wheel and broke it down. I just divided it by 5. And so then you get steps of 72 per color. So the lowest wavelength radio data gets red, and then you move up 72 color units into the green, sort of orangish green, to get to infrared, and then optical, and ultraviolet, and X-ray. So it's really basically a simple application of this idea of how to apply color to the data. And now we can step through each one and see the Crab Nebula. This is a neutron star pulsar at the center here. Again, it's another supernova remnant. There's a disk of materials swirling around this, and this is, again, all X-rays, so very high energy. This material is swirling around the star. There are jets coming out of it, and it's basically the heart, the engine of this whole supernova remnant. It's just irradiating everything around it. So as we step down in energy, shift in wavelengths, now we're looking at ultraviolet light. And that starts to show more of the interior of the nebulous structure surrounding the pulsar. Now with Hubble and its superb resolution, we're seeing filaments of material that were ejected from that star and are being irradiated by that core. And you can kind of see a ghost of that core here, this sort of ghostly glow in the middle here. That's, again, coming from that neutron star and its swirling disk of material. As we shift down to longer wavelengths, lower energies, now we're looking at warm dust. So this is kind of tracing those filaments as well. And then when we get to radio wavelengths, we're actually looking at more of, we're getting an understanding of the magnetic fields that are constraining all of the material in the supernova remnant. And so now this is a really great example of why it matters to look at the universe in multiple wavelengths. Having all of this information and being able to see it all at once gives you a much different picture of what's happening with this object. Now here's a really good one. I just put this in here yesterday. This is a press release from yesterday of Eta Carina. This is 7,500 light years away in the Carina constellation. And basically there was an explosion about 170 years ago And there's this sort of bipolar outflow coming out. There was a triple star system. We think maybe one of the stars absorbed the other star and created this explosion. So now there's a binary system in here. The really interesting thing about this new image that just came out yesterday, and it's a celebration of the 4th of July, the blue data here, this is all new. This was just taken last year. And it's highlighting magnesium. And I should say this is just Hubble data. This is just an optical image. We're not looking at X-rays or anything like that. But this was the first time that we were able to see material sort of between we call this the homunculus, between the homunculus and then the surrounding nebula in the red. We always thought there was sort of this gap between the two, but now it's actually filled in with magnesium, magnesium light. And it was made possible by taking a really deep look at this object in that filter, which is an ultraviolet. So it's a pretty high energy filter in Hubble terms. And it has implications for our understanding of these kinds of objects elsewhere in the universe. I've been talking about these H2 regions in galaxies, these red dots that sort of highlight star formation. Well, it's possible that there are these mag2 regions elsewhere as well that kind of highlight another aspect of this kind of formation. And one thing I wanted to do with this, which is really fun, and I could do this for any image, but I thought this would be cool. Let's take a step back and see where this is in the sky, right? There's the Milky Way galaxy. This is a beautiful image made by Nick Reisinger. He actually traveled the world to take this image over the period of about a year. Took images all around the world and stitched together this huge panoramic image of the Milky Way galaxy. And this isn't even the whole thing. It's just a piece of it. But that region we were just looking at is contained within that little box. So now let's zoom in on that box. This is a digitized sky survey image of that region. So this is the Carina Nebula here, this sort of whole structure. Now we can zoom in even further. This becomes like fractal. This box here corresponds to a famous Hubble press release image from a few years ago, the Carina complex. And now contained within this image is Eta Carina, the image we were just looking at, in this little box right here. Now we're back. And since we've been talking about multiple wavelengths and multi-wavelength astronomy, let's back out and take a look at it in this context when surrounded in X-ray light. So this is that same region. This is Eta Carina now, same color composite, but now we've also overlaid it with X-ray light. And so the X-rays are actually emitting sort of outside of what we were looking at before. This is, again, it's hot gas, and Eta Carina, the Hubble image, sits inside of that. Then we can take that away. You can see in 3-color. Now, that core there is really high energy X-ray. It's blue light. This is the same kind of 3-color red, green, and blue combination as I've been talking about before. So that core is very highly energetic. It's emitting a lot of X-ray light, and it's irradiating the surrounding material around it. And that's hot gas emitting X-rays at lower energies. Now let's shift back down. Now we're looking in optical light again. This was Hubble's anniversary image from last year, 28th anniversary image. This is the Lagoon Nebula, or Messier 8. And this is a great example of Hubble's capabilities as a multi-wavelength observatory, because we also looked at it in infrared light. So that's the infrared view of this same region of space. When we look at it in infrared, we actually peer through the dust and see the background stars behind this nebula. And only the densest regions, the densest clumps of materials remain in infrared. Sort of this ghostly glow of dust here. And this highlights the importance of the James Webb Space Telescope, which will be launched in March of 2021. That is going to be an infrared telescope looking at the universe in infrared wavelengths. One of the main science drivers for the Webb telescope is peering as far back as possible to the furthest reaches of the universe, looking at the first galaxies. And the reason we need infrared to do that is because those galaxies, although we look at them, we look for certain markers in optical wavelengths, the universe is expanding and its expansion is accelerating. And so the most distant galaxies are emitting that light in infrared wavelengths because they're actually red-shifted, sort of like Doppler shifting. The light that's coming out of them is being shifted into longer and longer wavelengths. And so the light that we would typically look for to study those galaxies has moved from optical to infrared. So now we need something with Hubble's superb vision that can see in infrared, and that's what the James Webb Space Telescope will do. So, what to take home other than your personal belongings? Light is more than meets the eye. It's information, and it surrounds us. Right now, we are in a golden age of astronomy. We are looking in every possible wavelength, even beyond the electromagnetic spectrum. We now have what's called multi-messenger astronomy. We're understanding the universe in ways we never thought possible. Gravitational waves are giving us a new insight into the universe. Light is the key to understanding our universe. And now I've been talking about all these images, the way I've been applying color to them, specifically like the X-ray images. You may have heard the term false color when they're describing X-ray images, right? Don't listen to that. False color is bad. And that's the essence of the title, Translating Cosmic Light, is really about the images and how they're created. Translated or representational color is the preferred nomenclature when discussing these kinds of images. The term false color just perpetuates this idea that the images are somehow fake, that we're making it up, that it's not real. Translated color is really what we're doing. We're taking light that we can't see with our eyes and translating it into something that we can see and understand with our eyes. And so for more information, I need to update this slide. Hubble site doesn't look like this anymore, but this is where you can go for all the latest Hubble news. And I also run a blog, and Frank also contributes to the blog, called Illuminated Universe, where we take a behind-the-scenes look at a lot of like what I've been talking about tonight, sort of how the images come about, how they're created. A lot of times we make editorial decisions in our news meetings where we've created certain products that just don't fit the story that we're trying to tell for that particular press release. But this gives us an opportunity to put that information out there as well. There are images that I've created that don't have a home, so Illuminated Universe is where they go. And I hope you enjoyed taking a look at Illuminated Universe. Thanks. I'd be happy to take any questions. Thank you.
Grant has the microphone. Who's got questions?
Hold up. You got to say it into the mic. We have an online audience. Ready?
Is the Webb telescope, is it only infrared?
Yes.
Only infrared,
Only
so
infrared.
no other, okay.
Yeah, it overlaps a little bit with what Hubble does, because Hubble goes out to infrared as well.
Mm-hmm.
But it's an infrared telescope, yeah.
Okay.
You got first, then you.
So in some images, like, would you prioritize like a certain group of data more than the others? Like, if X-rays showed more of what you were trying to get at in that image, would you like make those clearer and then kind of dim the visible light kind of stuff?
Yes, so that has come up in the past where the X-rays are telling a certain story. And actually what really happens is sometimes when we're combining all these different wavelengths together, we run into a situation where we're oversaturating certain areas of the image. And in those cases, I will take some liberties with adjusting the levels of different components of the image so that you can see everything that's there.
Yeah, and I like what you showed Cas-A here,
Yeah.
where Hubble is good in Cas-A, but the X-rays are amazing in Cas-A, right?
Yeah. Let's look at it again.
So sometimes when you give talks to public audiences, they're kind of surprised that Hubble doesn't always have the most beautiful image of an object, right? If you go to other wavelengths, you actually see a lot more interesting structure.
Yeah.
In your experience, what has been the most remarkable discovery in contrast to a hypothesis that you have made when you have actually looked at it in terms of different wavelengths of light? I'm sure there's
That is a great
several,
question.
but what has blown you away the most?
I would say that Crab Nebula image that I showed, that really blew me away when I pulled all the data together and saw That. Yeah. When I put it all together and that showed up on the screen, I just was like in shock. Because working with the Chandra X-ray Observatory for 15 years, I had seen the Crab Nebula many, many times. And I always saw that. That was my view of the Crab Nebula. And then, of course, there's this amazing Hubble image of the crab. But seeing everything from radio to X-ray all together in one image just blew my mind.
And as a scientist, how much of a rush is that? I mean, how many nights did you stay up going, man, that's so cool?
Oh, yeah, it's a huge rush.
We sometimes, will admit that, yeah, we do have a fun job.
Yeah, Frank and I geek out a lot.
All right, so we have a question online, which is sort of the same. It says, which is his favorite Hubble photo? And I guess you could also include Chandra in there, too, since you've worked Chandra more years than you've worked for Hubble.
I have, but, since I've been with Hubble, the Lagoon Nebula is definitely my favorite image so far. And I've been here for 2 years now. And again, seeing this materialize on my desktop as I was working on it was just a rush, like the Crab Nebula. Yeah, it was just an amazing experience.
What is the best way to take a picture of the Milky Way?
The best way to take a picture of the Milky Way?
Yes.
All sky?
Yeah, probably what that guy that I was talking about, Nick Reisinger, who traveled the world to take a picture of the Milky Way, because that's the only way you can take a picture of the entire Milky Way. Because if you're only in the northern hemisphere, you're only going to see a certain portion of it. So being able to travel the world and get the whole view, that's the best way to do it. It's very expensive.
What's the farthest object that the Hubble Space Telescope has ever seen, and would the James Webb Telescope be able to see farther?
Yes, the farthest object Hubble has seen was 13.4 billion light years away, I believe, give or take.
13.2, around 13 billion.
13 billion light years.
It's kind of, our uncertainty grows when we get to that level. But yes.
Yeah, but so for Hubble, that is just like a faint red smudge in an image. Webb will be able to resolve more detail out of that. Not a lot of detail.
Yeah. I mean, when we talk about JWST, we often talk about probing the first billion years of cosmic history. And that by looking into the infrared, we will see things at just slightly larger redshifts. So we will be able to see things into, almost to the first galaxies that form, right? We're seeing, toddler galaxies. We want to see the baby galaxies, okay? And that's really the promise of looking into the infrared, is we will be able to see that light, which gets redshifted all the way into the mid-infrared.
Yeah, so Webb will be able to see further. Billion,
yes.
Are you able to pull up really quick the pic of the deep field, the Hubble deep field?
Yes.
Because my question goes right along with what the last question was.
Yes.
Somewhere in there is the red dot that science has told us that's the farthest galaxy that we can see. Out of that picture, if you can go back to it again, out of that picture, how does science determine that's it? That's the oldest thing that we've seen. How are you able to determine that?
So when we take these data sets, it does make a beautiful image, but there's also more data there than just the image. There's spectroscopy, and we're able to do spectroscopic redshift studies of the galaxies from the image. And so we can actually pull out, we call them postage stamp images. We actually have software that will go through the image and analyze it and pull out each individual galaxy and create a little image of that. And from that image, be able to determine the redshift of that galaxy, basically. And that gives you a distance estimate for it. And so when you look through this image that way, in that method, that red dot becomes the farthest object. I think so, but on this screen, you're probably not going to be able to see it.
Yeah, and this is the one with the ultraviolet added to it, so it's hard to pick out the red dots in this version of it.
Right.
Okay, we got a question from online. that says, how long does it take for you to prepare one of these images?
I believe that's it right there.
That's one of them, yeah.
Yeah. How long does it take? Yeah, that's a good question. Some of these images can take, I can do it in an afternoon. Some can take a week to a few weeks. Depends on the complexity of the data set. A lot of Hubble's like really famous images are actually mosaics, which means Hubble goes and takes multiple images and stitches them together. Well, I stitch them together. And in those ones take a lot more work. There's a lot more pre-processing to get the mosaic image looking nice. And then putting it all together, it becomes a very computationally intensive thing as well, because these images are like billions, well not billions, but millions of pixels across, and you end up getting Photoshop files that are like 10 gigabytes in size, and it just takes a long time to deal with them. So yeah, there's a big range in the time it takes.
You mentioned images being north up, and I think of north in reference to our poles. How is north oriented in space?
So imagine taking latitude and longitude of Earth and just extending it out into space. Then it becomes right ascension and declination, and there is north and south to that. And so, the images that are north up are.
Yeah. But if you're in the southern hemisphere, your natural orientation would be south up, because everything rotates around the southern celestial pole, versus here, everything rotates around the northern celestial pole, right?
See, there's no up or down.
Yeah, there is no up or down, you know.
Making me work tonight.
Based on your formation of these images, would you consider yourself an artist or a scientist?
That's a great question.
The answer is yes, right?
Yes. It's both. I feel like I get to exercise both halves of my brain when I work on an image, because there's a scientific aspect to it. There's the data preparation, the pre-processing, and then also as I'm processing and moving into the realm of art, I'm also keeping in mind the story that's going to be associated with this image, because every image has to tell a story. It has to be a part of a press release that's telling a story. Like that Eta Carina image, the blue data there, that's the key to that image. And so when I was processing it, I was keeping that in mind as I went.
Grant, we have a question in the center as well.
So you mentioned there's a wide dynamic range on the sensors themselves. Actually, how wide is it? Like 0 to 24-bit, 32-bit?
They're 32-bit images, yeah. So
from the Hubble itself.
Yeah, but the detectors, the original detectors were only like 65,000, whatever that. Yeah. For some of them,
Have
but
they upped it on the Webb telescope?
it's the CCD charge count of the detectors, which was in the tens of thousands for the original Hubble images. I don't know what the current stuff is.
I know that the FITS files that you download from Master are usually 32-bit.
Yeah.
I was wondering if you could explain, or when we get around to creating the W1 telescope after James Webb, I know I'm jumping the gun here. Will W1, which has a huge field of view, will that make your job easier? And how will we ever process, I mean, it must be huge banks of data. And I guess that's a problem they'll be resolving as time goes on. But how will that affect your job, being able to pull up that?
That's future Joe's problem. So. No, but you're right. The W1 telescope is, it's an infrared telescope that has a field of view that's 100 times that of Hubble's. So every image that it takes will be 100 Hubble's, essentially. So every time I deal with one of those images, it's going to be a huge mosaic, multi-gigabyte image file. So it's going to be a real challenge, and we're kind of working with the instrument teams to figure out how we'll actually deal with a volume of data like that. Right. It may actually end up being cloud computing that we do for that.
Right. I mean, this is a thing in a lot of astronomy. We're getting these very large surveys, the dark energy camera that is like 520 million pixels per image. 520 million pixels per image, okay? These are getting to be more and more common in astronomy. We're going to have the LSST, which is going to take, petabytes a night or something like that. I don't know.
All sky images every
all
day.
skies images. Okay. Data processing is a huge thing. So all of you young kids that are out here thinking, data processing and data analytics, it's a huge burgeoning field because it's not just in astronomy where we have way too much data to deal with. We're developing it all over, and yeah, it's going to be fun.
Thank you, President Joe.
You're welcome.
Hi.
Hi.
So it's my understanding, like with the Hubble, it's like looking at a really small portion of the sky, but just looking very deep.
Yep.
Is that correct?
That's
so,
true.
Are there? I guess does it ever get used to look at things that are closer, or are there just other telescopes that look like? Can we look at Pluto get a very good view of Pluto, which is much closer than like this stuff you're showing, right?
Yeah.
Like in order to, and like, can we? Are there telescopes like that? And do we ever look at like other solar systems to compare to ours and kind of see planetary movement and that kind of thing?
Yeah.
I guess that's my general question.
Okay. So this is actually a Hubble image of Jupiter here, taken 2 years ago. So Hubble does look at nearby objects as well. And you're right about the size. It's equivalent to looking through the eye of Eisenhower on a dime held at arm's length. That's roughly the field of view of Hubble.
Yeah, it's like 1/12 millionth of the entire night sky. Okay? 1 part in 12 million.
Frank has a really great blog post on Illuminated Universe plug about angular resolution and why Hubble can take an image of Pluto, but it doesn't look very good because Pluto is a very small object and it's relatively distant in terms of where Hubble's looking. A galaxy like the Whirlpool galaxy is just enormous, like hundreds of thousands of light years. Not quite that big, but
like 65,000 light years
5,000
across,
light years across. So it's something enormous. You can see a lot of detail with that with Hubble. But yeah, check out the blog post.
Which part of the electromagnetic spectrum do you think takes the best images?
Visible, of course. Now that's a very subjective question.
I mean, I think as humans, we're used to the visible light, so we're going to favor that. But I got to say that I would love to see more work on radio images because radio images, you need to take like the VLA in several different configurations to get the detail. But radio images can have incredible micro arcsecond detail that Hubble can't have. And so some of the radio images, when they take the time to actually process them, are really cool.
Like the black hole in M87.
Yeah, right.
It's a radio image.
Yeah, so radio has a lot of potential that I don't think has been exploited enough by the radio community.
I have a question actually about the lithograph for both of you. Is the Ring Nebula sort of what may be happening with our sun in about 8 billion years, or is this the sort of thing that will be going on with our sun?
Yeah, well, it's going to puff up and cast up material into space. It's not quite massive enough to do much more than that. It'll just sort of peter out. I don't know, Frank, what do you think? It's going to turn into a planetary nebula?
The textbook answer that you will get normally from an Astronomy 101 class is, yes, our sun will go off and die by being a planetary nebula. The research level answer is probably not quite as pretty as the Ring Nebula, because it looks like you need about 1.5 to 2 solar masses to really blow off a planetary nebula. That's still uncertain right now. It's still subject to research, but the folks I've talked to say, yeah, the sun's not going to go planetary like that. It'll still have mass loss, but it won't be a nice, beautiful nebula. Shh.
So, about how many galaxies was Hubble able to identify since its launch?
Since launch?
Well, let's see what the
Let's
candles
just take,
field.
yeah, the candles, all right. Yeah, take the candles field.
So this one deep field image that we've done with Hubble had, 65,000 galaxies in it, I think?
Yeah.
And that's just one image.
No,
It's
I'm
one
talk-
very deep image.
Yeah, no, I'm talking about like naming them actually.
Oh, naming.
We don't name them.
Yeah.
They get catalog numbers.
Yeah.
Okay. Yeah. So if you're in the Hubble Deep Field, you'd be HDF, and then it'd be your RA and your DEC as your catalog name, unless there's a specific reason. I mean, what the Sloan Digital Sky Survey has how many millions of galaxies in it? Yeah. I mean, when you get up to millions and such, you can't name them Jeff and Fred. It just gets a little tiresome to try and do that.
How did you decide that this is what you want to do for a living, like editing and taking these pictures and processing them?
Oh, yeah. Good question. I always loved astronomy as a kid. Growing up, I just was fascinated with the stars. And then when I went to college, I studied astronomy and astrophysics, and I thought I was going to go the PhD route and sort of become a professor or something. But after I graduated from undergrad, I was doing research work. When I was at Chandra, I was doing calibration and instrument operations for the Chandra telescope, and I loved that work, but it wasn't my calling, I think. And I always had this sort of artistic side. I did painting. I'm a musician. I wanted to engage that as well as a part of my career. And so an opportunity arose when I was at Chandra to do image processing for public outreach, and I jumped on it. And then through that, my experience there with 8 years, sort of made connections with people at Space Telescope, and then was able to come down here. So it was always there, and it was just being able to figure out the path to get everything together in the same job.
Yeah, and since we have a bunch of the CTY students here today, sometimes they call CTY Geek Camp, right? Okay, you think you're geeks, you can also be artistic, okay? Joe and I are two people who get to do some really geeky stuff with the Hubble Space Telescope, but we've worked on IMAX films together, okay? We get to work on movies and visualizations and artistic things. We get to work with Ann Field, who's a wonderful artist. We get to work with, writers and designers and everything. You can satisfy both your artistic side as well as your scientific side in your career. So do not limit yourself, okay? I always like to tell the kids that because, don't think you have to be one or the other. You really can do both.
Do you think that there's a possibility in the future that we will launch another gamma ray observatory or radio observatory after Compton shut down in 2000? Do you think there's a possibility that might happen again in the future?
I believe the Fermi telescope is actually also a gamma ray telescope. So there is a telescope currently operating that's looking at gamma rays. It's just not one of the great observatories.
It's just a pretty good observatory.
Pretty good.
No, Fermi is wonderful, okay? But it's just not in that, I don't know, branding.
Yeah, branding, exactly.
Who we got?
So you receive images that are black and white. Do you spend a lot of time processing and working with the black and white, and then all of a sudden you start to add color to it? So you spent hours maybe in black and white before you see the color?
Sometimes, yes. I'm actually working on an image of Jupiter that was just taken a few weeks ago right now. And in that case, yes, I've been working on it in black and white. The challenge with making an image of Jupiter is that when Hubble takes the 3 images to make a color image, Jupiter is moving so fast that it changes while it's taking the data, right? So to make a color image, you have to sort of account for this slight rotation and the movement of Jupiter as it's being photographed. So that takes a lot of work in black and white to get everything lined up. I mean, I'm essentially like warping clouds in Jupiter and lining them up in black and white and then applying color.
Question from online, what instrument do you play? And go ahead and plug your band if you'd like.
I play guitar. My band is called Riding Shotgun. Check out ridingshotgun.com.
Shameless plug.
Are you related to the violist, Joseph DePasquale? Do you know that?
I am not. No, I get that a lot. My dad is also Joseph DePasquale, and we used to get phone calls when I was a kid asking for the violinist.
All right, just a couple more questions here.
All right, well, I guess I have a second one here. So I'm wondering if you have seen images that then make you go, hey, wait, this doesn't agree with, our current understanding of physics. And, how do you guys go about, do you have to like contact someone else and say, hey, what do you guys think about this? And kind of like, have you run into anything like that in, all the stuff you've seen?
Yeah, so I have a good example with that. I don't know how great I can explain it off the top of my head, but when there was a gravitational wave event in August 2017, Hubble took some data of the object. It's called a kilonova, just an enormous explosion, and it was looking in infrared in two different filters, and we were making color images of that object spaced out by a few days at a time. And what I noticed was the first image, the object appeared to be sort of yellowish, and the second one it turned blue, which was kind of surprising, and then the third one it was back to being yellow but dimmer. And it turned out that in that middle observation there was a slight gap in between when the two different filters were taken, and it was just long enough that the object had actually dimmed enough to allow the shorter wavelength to be brighter than the longer wavelength. And so the color changed, and that was a surprise. And so we usually are working with we call them the principal investigator, the scientist who took the data when we make these press release images. So we went back and forth with the investigators and determined that, yeah, there was this issue where there was a separation that shouldn't have been there, but unfortunately was, that caused this change in the color. It's not intrinsic to the object. It was just because of that break. Yeah. And so that was a case where there was something surprising. We talked to the scientists about it. We figured it out. And then we ended up just releasing it as a black and white because the whole goal was to show that it was dimming over time quickly. I hope that made sense.
Okay. One comment from online says, riding shotgun could use a good tuba player. I love the internet.
Hi. So we have these telescopes that we can take a look at pretty deep and far away object in space. What do you think personally is the most important takeaway or most important thing we can learn from these images? Because they're pretty far away and we probably won't get to them that easily. So what do you think is the most valuable thing that we can study from it?
Well, I think every time we look at something, we're just trying to deepen our understanding of the universe in general. I mean, you're familiar with this Carl Sagan quote that we are star stuff. We're made of the materials that were generated, forged in the hearts of stars that exploded billions of years ago. And also, taking that a step further, we are the universe trying to understand itself. And I really love that concept of the material of the universe becoming conscious and trying to understand itself and looking out and peering into space. So it's sort of a way of humanity trying to understand itself, the universe trying to understand itself, all sort of wrapped into one. So it's it's like the most fundamental questions that we have, we're trying to find answers to when we look into space.
Thank you.
Okay, we got 1, 2, 3, and then we're done. Okay, because we're going. I know we can get these guys asking questions forever, but go ahead.
So, what were your thoughts on the black hole image that we recently got earlier in the year?
Oh, I thought that was incredible. That was an amazing image. I wish that there was a little more providing context of where in the universe this object actually was and what it looks like in other wavelengths. Because I work so much in multi-wavelength, I wanted to see that image of the donut in context with everything else around it. But otherwise, yeah, it was just an incredible achievement to be able to take that image.
Definitely.
All right, so I was just wondering, you said it had like terabytes of data and stuff. So I was wondering how long it takes to transmit all that data from the telescope to the computer that you're using to process the images.
Right, so the data actually on the telescope is stored on, there's basically hard drives on the telescope, And it's not terabytes of data that are stored on the telescope. It's just over 29 years worth of observations, we now have terabytes of data. At any given time, there's probably megabytes to gigabytes of data on the telescope itself that are transmitted down through NASA's Deep Space Network, a series of satellite dishes. And then they make their way here to the multi-mission, the Mikulski Archive at Space Telescope, MAST. And that data is available to anyone who wants to take a look at it. mast.stsci.edu. I think that's the URL.
It is, however, a very geek-friendly website. It's not a user-friendly website. It's for scientists by scientists. All right. There was one. Yeah, the context of the black hole, I put it's on our Hubble site YouTube channel. So on our Hubble Space Telescope YouTube channel, I made a video zooming in just to with a series of stills. Actually, I showed it at the public lecture series just to give context on that, because we here were unhappy that it didn't, that the press release that from the official team did not have enough context. Yeah, last question.
So you stitch together images in color. So Hubble takes images in black and white. Would you say the color images that you stitch together are more or less useful than the black and white images that are taken by Hubble?
That's a good question. So to the scientists, the black and white, the data, the raw data is what they're looking for. It's the most useful for them. But there have been cases where I've worked directly with scientists to make an image that is then used for analysis, or it becomes a part of a paper. So it goes both ways. Sometimes the color image reveals details that are not immediately obvious by looking at the black and white data. Because you have more than one image together, you can actually see more at one time. So yeah, it kind of goes both ways.
All right, I'm sorry that I have to cut it off there, but conversations like this. All right. Please join us in August. We will see you then. Thank you all.